Hi everyone. So even though today is the day one lecture, I'm gonna give you a full lecture because this is the video recording lecture, and we're gonna count on the your participation from next week after the confirmation of the your subject list. So yeah, we'll just provide full lecture for the first week, and even though you enroll this course in the next week, you can still listen to this video lectures. Okay, so please understand. Yeah, please. Typically, for the first lecture in offline course, yeah, I'm gonna give like a 20-minute and 30-minute lecture and just make some joke and close the lecture. That's my typical habit, and most lectures goes like that if it's first lecture. But most of you are like a freshman who went through the COVID-19 online lectures for the entire year. Yeah, it would sound quite weird, but hopefully, yeah, you can come back to campus on fall semester and try to get one free lecture as a introductory first day one lecture. But anyway, yeah, now we are doing video recording, so let me give you a full lecture from day one. So the topics that I'll cover today is following. So I'll talk about statics, and I'll talk about two force members, and I'll talk about reliable design. So I'm not gonna get into full details, but want to give you some brief introduction about review of freshman physics and a little bit smarter way to solve a statics problem, which is two first member, and based on that, how we can say a design is safe or not, whether the design is reliable or not, okay, based on the stress obtained from statistics analysis and the material property. Okay, so let's begin from one example problem we're going to consider today. So this is the example problem we're gonna consider. Even though I'm gonna tell you that I told you that we're gonna consider deformable body for the day one lecture, let's consider rigid body problem in most part of the day one lecture because we are giving a review, and for most lectures and for most problem we're gonna consider the wall is rigid wall. Okay, if we allow the deformation of the wall, yeah, the problem becomes much more complex. So in the most homework problem and example problem we're going to consider in ME231, we'll assume the wall is rigid. Okay, we'll consider deformation of structures. Okay, so this problem asks this question: what will be the force acting on road BC? This is the road connecting BC, so we call this as road BC. So I don't know why, but somehow our textbook calls a beam with a circular cross section as road, and beam with rectangular cross section as boom. So I don't know why, but I'm not American, so I'll just follow their naming. So, and we have A point here and B point. So the problem asks also the force on boom AB. Okay, and the problem also take coordinate system as XYZ in this way. X is horizontal axis, Y is vertical axis, and Z is the axis out of this plane, out of this paper. Oh, not paper, it's electric screen. And so I think most of you may see a LED screen, so out of your LED screen. Okay, and the dimension is given as 800 millimeter and 600 millimeter, and the force is acting on this weird structure with 30 kilonewton. And if we this structure from the side, this is your eye, and you are looking at here, so you have boom AB. This is boom AB, and this is road BC, and boom AB and road BC have a hole, and this hole is connected by pin B, which is colored as black. Okay, and they are freely rotatable, even though it's freely rotatable, and they are making the mechanical equilibrium out of this ABC structure. So the pin stays there under mechanical equilibrium. So the step-by-step procedure that we have learned in freshman physics is following. So for the entire structure, what we have to do first is we have to find number of degree of freedom. So regarding number of degree of freedom, you can think about 3 degree of freedom about translation along XYZ, and rotation about x-axis, rotation about y-axis, and rotation about z-axis, rx, ry, and rg. Okay, and second thing you have to do is you have to find and specify all unknown external forces components of whole structure. Okay, now third step, you have to write down mechanical equilibrium equations such as force equilibrium and torque equilibrium. Then you're gonna get like a number of degree of freedom equations. Okay, so you have to have your equation, a number of equation more than this external unknown external force. And if you found that this number of degree of freedom is smaller than number of unknown, you have to repeat this step 1, 2, 3 for individual segments. Okay, so even though this 1, 2, 3, 4 step gives the review of entire freshman mechanics, but if you look this, it doesn't sounds real. Okay, I mean it's too abstract. Okay, so let me give you just an example. Okay, that will give you much better sense on what's going on in this 1, 2, 3, 4 procedure. Okay, so let's first consider step 1. Let's find the degree of freedom. So as I told you, we're gonna assume a rigid wall. Okay, so we have this A, B, C structure. Out of this A, B, C structure, we're not gonna allow translation in along z direction. We're not gonna allow rotation along about x-axis, rotation about y-axis. We'll only consider rotation about z-axis. Okay, so this is the z-axis. Okay, and we are considering rotation here or there. Okay, so if mechanical equilibrium does not satisfy, this structure can move up and down or rotation. Okay, so this is the degree of freedom we're gonna allow about ABC structure. So the total number of degree of freedom is 3. Translation along x, translation along y, rotation about z-axis. Okay, so 3 degree of freedom. Now, step 2 for whole structure, rod BC, boom AB, pin B. So we are combining these 3 as a whole structure and try to draw free body diagram. Okay, so we take this whole body structure and try to specify all unknown forces. Okay, so out of this free body diagram, if this 30 kilonewton comes out of this thing, okay, so we have 30 kilonewton here at B point, and about A point and C point. Yeah, we know that there might be force along x-axis, force along y-axis, but we don't know how much force are there. Okay, so in total we have 4 unknown forces: ax, ay, cx, cy. Okay, so we find that number of unknown is 4. Okay, so if you compare number of degree of freedom and number of unknown, we find that there are more unknowns than number of degree of freedom. Step 3 will be write down mechanical equilibrium equations. So for each degree of freedom, we can write one equations. So let's take RG first. So we're gonna take rotation like a counterclockwise as positive sign. This is the sign convention we're gonna take in this course, and this is the sign convention of most freshman course and freshman physics course and most solid mechanics course. If we take this as positive sign and try to get the moment or torque about c-axis, and this sum of the moment should be 0. And if we write down here, so ay is along this c-axis, does not contribute the moment or torque. Somehow, instead of a torque, we're gonna call the torque as a moment in our course, and we'll consider twisting torque as torsion in our course. Please remember the distinction between the name. Okay, so the torque summation, moment summation about c must be 0. So you have ax multiplied by 600 millimeter, which is 0.6 meter, which gives positive contribution because you are considering torque around the c point, and we have clockwise torque or negative torque minus 30 kilonewton multiplied by 0.8 meter, 800 millimeter. So after this equation, you figure out ax must be 40 kilonewton. Okay, now let's consider translation in x, or by taking right direction as positive sign and try to sum up all force in horizontal direction. Force sum should be 0 to make mechanical equilibrium, right? Then along the horizontal axis we have ax and cx, so ax plus cx should be 0. So you figure out cx must be minus ax, which is negative 40 kilonewtons. Now about translation in y, typically we take upward direction as positive sign and try to see sum over fy must be 0. So there is 1, 2, 3 vertical forces ay, cy minus 30k Newton summed up to be 0, and we figure out ay plus cy must be 30 kilonewton, but that's it. So we have only 3 equations because we have 3 degree of freedom, but there is 4 unknowns and we need one more equation. So as I told you, if we found in this condition, we have to repeat this for individual segment. So let's take individual segment, which is boom AB, and try to draw free body diagram again. So we already figured out AX, which is 40 kilonewton in this direction, but AY and BY, BX, this is the force exerted by P and B, is unknown. Okay, so for solving this problem, what you have to do is, if we consider moment around this B point, in moment sum should be 0, and AY multiplied by 0.8 and put negative sign because this AY force gives clockwise rotation. We have to say this is a negative sign because we typically take counterclockwise rotation as positive sign. Okay, so minus AY multiplied by 0.8 meter must be 0. AY should be 0. Of course, force acting on B point BY BX does not contribute to moment. Okay, so because AY is 0, CY is 30 kilonewton. Okay, so with that, we figure out all unknowns AX, AY, CX, CY. Okay, so to summarize, if we consider the entire structure, these are the forces acting on A point, B point, and C point. Okay, this is about the entire structure. We can separate this into 3 structure. If we take out road BC, yeah, so this, if you combine 40 kilonewton and 30 kilonewton, it's same as 50 kilonewton. So what we have to figure out is due to pin B, road BC must get 50 kilonewton in opposite direction to make a mechanical equilibrium. This is the force diagram for road BC, and about the boom AB, it should satisfy 40 kilonewton compression because you only have force from left side, and force at right hand side, or which is B point, must be 40 kilonewton opposite side. Okay, so boom AB is under compression. Now, if we consider force diagram of P and B, you have to combine 40 kilonewton. Yeah, this 40 kilonewton and that 40 kilonewton, they should be opposite direction according to Newton's action-reaction principle. And this 40 kilonewton and this 40 kilonewton must be in opposite direction due to Newton's action and reaction principle. And this is 30 kilonewton. This is the force acted by this initial external force. Okay, so we see that, okay, it satisfies mechanical equilibrium. Okay, so with that, I can give you a very brief review of freshman physics or statics. Okay, so let me finish first part of lecture here, and in the second part of lecture, let me give you a little bit smarter idea to solve the same problem.